Yeah. We'll go. I bet. We'll do it. It was over at halftime. I know. I'm still nervous though. It's going to a bigger comeback. That's like the game. That's the joke I kept making. They said, Tom Brady came back from 25. It's like the script writers are making sure that Holmes comes back from 27.
Mhm. The assignment, that's the assignment. I think there's some the break on breaking.
Oh, really?
Someone like it. And. How like when you put the break is currently.
Yeah.
Relative force, I push down. And I'm broken down.
Oh
It was
my
like-
gosh.
It was like a older bike, but it was like a steel,
Dang.
Now it's like. I found out that. That's specific thing on where the crazy,
Yeah.
they're cast, and depending on the casting process, that's what they're doing, like a lot of, roles and just,
Oh, I see.
just passive work.
I see. Dang.
Yeah, it was pretty interesting to see the fracture. So,
Dang.
you know, when I saw the assignment about that, I crashed right after that.
Oh, man.
It was awful.
Hopefully they weren't too traumatic memories.
And then after the chopper frame, I had
Yeah.
a bike that had like that same frame, when I was living, so even more memories. So, appreciate
Just
that.
that's hitting all your
Yeah,
childhood trauma.
really appreciate that.
Nice.
So like the chopper frame, it's pretty cool.
All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Good to hear. All right, so this week's just a standard week. So we just have kind of two just lectures this week. So we are kind of continuing on. Where we are in the class right now, we're still kind of going over kind of the basics of ANSYS, the basics of FEA. So today we're going to be talking about boundary conditions. Now, boundary conditions is something that you guys have already done in activity 1 and activity 2. Particular activity 2, we did actually talk about these quite a bit. But today, we're going to get a lecture in terms of kind of what boundary conditions, what their purpose is, and the different types of boundary conditions that you can apply in ANSYS. This kind of gives you kind of the necessary background information on that. Okay. So our next ANSYS activity is going to be next Thursday, February 20th. Although I did just get an email this morning that our next activity is going to be cut a little bit short because the school is running a mandatory evacuation drill next Thursday. So I'm saying this now because I'm probably going to forget next Thursday, and then the alarm is going to go off, and I'm gonna be like, what the heck is going on? So hopefully at least I remember saying this next week. And then at 6:30, so we're gonna have the first hour is going to be fun. So we have 5:30 to 6:30. And then at 6:30, there's going to be a mandatory evacuation. So we have to get out of the room, get out of the building. Some person's probably going to be yelling at us from the hallway, but we have to kind of evacuate that. So next activity is going to be cut a little bit short. I'm hoping that we can kind of finish everything, at least all my talking portions before then. And then just like the last activities, you can kind of finish the rest of it on. So, okay. All right. Any questions I can answer before we get started for today? Okay, all right, so let's go ahead and get started. So topic for today is boundary conditions. Okay. So, like I just mentioned, we're kind of going through all of the basics that you need to, just to even get started with FEA, right? So, today we're doing boundary conditions. Thursday, we're going to be talking about material properties. And so, again, these are all things that we've done in the activities, but, I want to keep the activities rolling and, we're kind of catching up with the lectures. Okay. Okay. So last time we had a lecture, a week ago, we talked about meshing. So after you mesh your geometry for your finite element simulation, the next step is to apply boundary conditions. So boundary conditions is hopefully a term that you've heard of, before this class, especially if you've taken 438 or 538, the math class. The idea of boundary conditions is, pretty ubiquitous within kind of just math engineering, just in general. Okay. So the purpose of boundary conditions is kind of twofold. And so on the one hand, boundary conditions, when you're talking from a physical perspective, physically boundary conditions describe any external effects that are going to play an impact or play a role on the outcome of your FEA simulation. Because remember, a lot of times when you run an FEA simulation, you're running it on a part that's kind of in isolation, or at least that's what it looks like on ANSYS, right? So for instance, the bike crank that we just did, you're running a simulation on a bike crank that's kind of isolated, right? But in practice, that bike crank is not, is not existing in a vacuum. That bike crank is part of a larger kind of physical system. So it's attached to a bike frame. And it's going to be affected on by people kind of pedaling on it. So it's going to be, it's going to have forces on it, right? So these external effects are things like fixed constraints, fixed supports, forces, pressures, things of that nature. Forks you can put on there, load, any kind of loads, right? Any kind of external effects that were going to affect your system, right? So for a structural system, any kind of external effects that are going to cause your system to deform, to rotate, to move, right? So those are boundaries. Physically, that's what boundary conditions represent. Okay. So I think that's kind of a good place to start, because I think that kind of physically makes sense to people running a simulation. But boundary conditions actually serve a mathematical function as well. So mathematically, boundary conditions are needed to fully specify the solution to the differential equation that you're solving. And so if you think back to, when you learned about differential equations, you always have to apply things like initial conditions or boundary conditions to solve for the solution, okay? In fact, let me kind of show you an example. So let's look at a very simple differential equation here. So let's say we have d squared u dx squared is equal to 3x squared, right? So very simple differential equation. We don't even need the characteristic equation or anything fancy here. We can just integrate to find the solution, okay? And so if we integrate once, right? We integrate once on the left-hand side, we get du dx, right? So one of those that integral is going to cancel out with one of the derivatives on the left-hand side. On the right-hand side, we're going to take the integral of 3x squared, so that's going to be x cubed. Okay. Going to do our inverse kind of power rule there. But since we're performing an indefinite integral here, so we're performing an integral without a lower bound or without an upper bound. Remember, in these situations, we have to add an arbitrary constant. We have to add a C1 to the solution here. Okay, and then if we integrate this again, we can solve for u of x. If we integrate this again, we have u of x is equal to 1/4 x to the 4th plus c1x plus c2. Don't worry, this class is not going to transform into a math class all of a sudden. I'm just using this as a quick example, right? ANSYS is the focus of this class, but I'm just bringing this up just to show you the applications. Okay. So this is our solution. But you can see from our solution here that it's only valid up until these two, we call them arbitrary constants. So we don't know the value of these constants. And the way that we solve for these values is if we apply boundary conditions. Okay. So for instance, let's say that we have a boundary condition. Let's say u of 0 is equal to 18. So in other words, mathematically what we're saying is that when x is equal to 0, the function u must have a value of 18. So we're basically forcing this to happen. So we're basically saying that through this boundary condition, we're forcing this function to have a value of 18 when x is equal to 0. Okay. Okay, so let's go ahead and plug it in and let's solve for one of the constants here. Okay. And so if we say u at x is equal to 0, I'm going to take my general solution above and plug in x is equal to 0. We have 1/4 0 raised to the 4th power plus C1 times 0 plus C2. And this has to equal to 18. Okay. So luckily this is pretty easy to solve because everything with the 0 is just going to cancel out. So we have 1/4 0 to the 4th power. That's going to go to 0. C1 times 0. That's going to go to 0. And so what we get from this boundary condition is that C2 must have a value of 18. Okay. So if we specified one of the values of our constants through this boundary condition. Okay.
So now we know that C2 is 18. All right, and then the other boundary condition that we have is, let's say we have du dx at x is equal to 10. This is equal to -5. By the way, for this problem, I'm just kind of making up these boundary conditions just so we can solve this mathematically. But for ANSYS and for finite elements, usually your boundary conditions are going to have some physical backing, just like we did in activity 2. Okay. But for this example here, I'm just kind of showing you just the math. So I just made these up, but usually you're going to think of the boundary conditions a bit more above. Okay. So what is this saying? So mathematically, what this is saying is that we're going to specify the slope of the function at x is equal to 10. Okay. We're specifying this to be -5. Okay. So once again, let's plug in our general solution here. So we're going to take the derivative of our general solution. We're going to take d dx of 1/4 x to the 4th plus c1x plus c2. Okay. So before we plug in x is equal to 10, we're going to take this derivative here. And so what we get is x cubed plus c1. Okay. Now we're going to plug in x is equal to 10. That we get 10 cubed plus c1. This has to equal to -5. Okay. 10 cubed is 1,000. So 1,000 plus c1 is equal to -5. And so we can see from algebra that c1 is equal to -1,005. Okay, and so if we plug both of these in, we get our full solution. We have u of x is equal to 1/4 x to the 4th minus 1,005 x plus 18. So in this problem, we can see that the boundary conditions played a very important mathematical role, because without the boundary conditions, we wouldn't be able to specify the values of our arbitrary constants C1 and C2. All right, any questions on this example here? Okay, good. All right, so I brought up this example kind of for another reason. So if you notice from the two boundary conditions that I specified here, they do look different from each other. So one specifies the value of the function itself. The other one specifies a value for the derivative. And so that actually is kind of a good segue into the next part, which are the types of boundary conditions. Okay. So there are two main types of boundary conditions that we are going to concern ourselves with. So the first type of boundary condition that we'll go over are called constraint type boundary conditions. Sometimes you'll hear me call constraint type boundary conditions Dirichlet boundary conditions. So Dirichlet is kind of the way that I was taught, but you know, it's also not very descriptive in terms of what that is. And if you've known me for any long periods of time, one of my pet peeves in just science in general is that every famous scientist wants to name the equation or the theory after themselves. So like Bernoulli's equation or Newton's laws of physics, right? But I hate that because, you know, it doesn't describe to you what that thing or equation does. It's just very narcissistic of the scientist. So I hate it when scientists name things after themselves. So I'm trying to change things. So, you know, I'm going to try to call constraint type boundary conditions, but I learned it as Dirichlet. So you might hear me kind of slip and say that every. Okay, the second type of boundary condition that we're going to go over are called mode type. And the fancy name for mode type boundary conditions are Neumann boundary conditions. Now, obviously, these are named after the people who formalized the theory behind it. Okay, so Edward von Dirichlet and Jason Neumann. I just made those up. I don't know what they're first. Okay, so let's go over constraint type boundary conditions first. Okay, so constraint type boundary conditions are very important. They are needed in every FEA simulation. So every FEA simulation that you run, you need at least one constraint type boundary condition. So that's, you know, one thing to remember. And in fact, you know, if you don't have a constraint type boundary condition in your ANSYS simulation, ANSYS actually won't even let you run the simulation at all. Okay. So what is a constraint type boundary condition? Constraint type boundary condition is basically one that forces the primary solution variable to hold a certain value. Remember, we mentioned that we discussed a few weeks ago about this idea of a primary solution variable. So every type of FEA simulation has a variable that's solved for first. And so it's the first thing that's solved for in the simulation. So for a structural simulation, the first thing that's solved for is the deformation. And so what we say is that deformation is the primary solution variable for structural simulation. So other examples of the primary solution variable for a thermal simulation. For a heat transfer simulation, the primary solution variable is temperature. For a fluid flow simulation, the primary solution variable is velocity in that case. Okay. So for every type of simulation that you're running, it's always good to be aware of what the primary solution variable is. Okay. So for this class, for most of what we're going to do, it's deformation, right? So deformation is first. Okay. And so what a constraint type boundary condition, it basically enforces or forces the deformation to have a certain value at whatever locations that you specify. Okay. So we've used a constraint type boundary condition in both of our activities so far. Okay. It's also the most common one that you're going to use in all of your simulations, which is a fixed support. So a fixed support boundary condition is one where we're basically enforcing or we're forcing the deformation to be zero at the locations where we specify the fixed support. So that's probably the most common example of a constraint type boundary condition. So fixed support, forces the deformation to be zero. Zero is a valid value. And so any boundary condition that forces the primary solution variable to have a value and you directly specify that value, right? So that's important. And so you have to be in control of what that value is. That is a constraint type boundary condition. All right, so actually, linking back to the example that we did earlier today, one of the boundary conditions that we did was a constraint type boundary condition. Okay? So if you look at the first boundary condition we did, which was u of 0 is equal to 18, right? So in this boundary condition here, from the problem, our primary solution variable here is u, right? That's the first thing that we're solving for in the problem. That's what we get our solution to be. Right. And so with this boundary condition where we're forcing the value of u to take on a value of 18 when x is equal to 0, this is kind of textbook definition of a constraint type boundary condition. Any questions on this so far? Okay, good. All right, so like I mentioned, a constraint type boundary condition is needed for every FEA simulation. So let's kind of talk about the physical reasoning behind that. And so if you don't have a fixed support, and so you have no fixed support that's present, there's really nothing that's preventing any kind of rigid body motion or any rigid body kind of translation or rotation. Okay. For example, let's say that we're doing just a very simple simulation of a beam. All right, so a beam looks something like this, right? Normally the beam is fixed to the ground with some kind of pin support or some kind of fixed support. Right, so we'll say it's a pin support here. The other side can be a roller, that's fine. Okay. So the fact that the support on the left is fixed to the ground, right? That prevents this entire beam from kind of moving and translating, right? Right? And so if we were to apply a force, so let's say that we apply a force going in this direction here. Okay. The beam would deform, right? So because of the roller support on the right, the entire beam should compress and kind of do a squish, but the entire beam is not going to roll away or translate away because of that fixed support. Okay, so when you're running your simulations, and usually it's pretty hard to forget, but it's important to remember kind of the role that it plays. Make sure that you always have at least one fixed. If you don't have a fixed support boundary condition in your simulation, ANSYS will throw a fit, and so it will tell you that you can't do this. So just kind of make sure that you. There are other ways to fix your model, so you don't explicitly need a fixed support. But there needs to be enough constraints on the model itself to prevent any kind of rigid body motion. So it's possible to provide enough constraints from the other types of boundary conditions. Technically, you can actually do it with force loads as well, but normally it's very difficult, especially for more complex cases. Okay? But there is another type of constraint boundary condition that you can do. We're not going to use it too much in this class, but sometimes it makes sense for certain applications. So another constraint type boundary condition that is available in ANSYS that does make sense in some situations is what's called displacement boundary conditions. So it is possible to use all constraint type boundary conditions to fully constrain your model. It's just a little bit more complicated. So the simplest thing is usually to apply a fixed support. And a lot of times physically that makes a lot of sense too when you're thinking about when you're thinking about kind of how your model is kind of fixed in reality. But sometimes it doesn't. And so actually, a few people kind of asked me last week if, instead of a fixed support, what if we apply kind of a cylindrical support or a displacement support on the three kind of holes that kind of fix the bike rack? And yeah, that's definitely possible. And so, some situations may call for certain things, but usually a fixed support is kind of the simplest way to accomplish this. Okay. Any questions on this so far? Okay, so that's constraint type boundary conditions. Let's move on to the next type, which are load type boundary conditions. So load type boundary conditions, the majority of the other boundary conditions that are available to you in ANSYS kind of fall into this category of load type. Okay, so it's kind of hard to come up with a definition that kind of encompasses everything. But kind of the best one that I came up with is just any kind of external effect that's going to have an indirect impact on your primary solution variable, I count those as mode type boundary conditions. So things that you can do to your model that you know are going to have an impact on the deformation, that you know are going to have an impact on stresses, but oftentimes is kind of the effect is kind of indirect. Okay, so most common examples that we're going to do in this class are things like forces, pressures, bearing loads, gravity. Right? So all of these things, you know, we know that if you take an object, you apply a force to it, it's going to deform, stresses are going to develop, right? But the exact relationship between, you know, force applied and the resulting deformation is not 100% clear, right? Versus when you apply a constraint type boundary condition, you apply a fixed support, you know exactly what the deformation is going to be. It's going to be 0, right? So any kind of external effect that kind of has an indirect impact on the solution variable, I count those as mode. Okay. Okay. So the most common way that this is applied mathematically is that these kind of take the form of a derivative. And so of course, you know, if you remember from the example we did earlier today, we did have one example of this, which was the second boundary condition. Okay. Right, so if you remember from that example, we had another boundary condition of du dx at x is equal to 10, equal to -5. Right. So of course, you know, this boundary condition is going to have an impact on the value of u, okay, at the boundary, but the exact effect is kind of indirect. And so it's indirect in the way that we're doing it by specifying the derivative instead of the value of the function itself. Okay. So with mode type boundary conditions, another thing that's commonly incorporated, not in the mathematical example that we did, but another thing that's commonly accounted for is the material properties and the geometric properties of your CAD file or your geometry. That's different from the constraint type boundary conditions, because the constraint type boundary conditions, you know, they're going to have the same effect no matter if you're doing it for steel or you're doing it for feathers or you're doing it for plastic or whatever, right? The constraint type directly specifies the solution here. But for a load type, because it's indirect, it's going to be affected by the material properties or the geometric properties, right? For example, so let's say that we have a beam here. It's going to be fixed on one side. If this beam were made of steel, you can apply a force, again. Let's say we're applying 100 pounds. So the 100-pound force here, that would be our load type boundary condition. And so for a steel beam, that's for 100 pounds, a steel beam, ideally, if it's casted well, is not going to deform all that much, right? Versus if you apply the exact same load type boundary condition to, let's say that we have a beam here, same geometric properties, but let's say it's made of plastic instead. And let's say that's the cheap plastic that's made out of your water bottles, okay? And so if you take 100 pounds and you apply it to a water bottle, it's probably going to break and crumble and kind of wish it didn't have 100 pounds on it. So the exact effect or the exact impact of the load type boundary condition often depends strongly on the material properties of the subject, right? But again, that's not the case for a constraint type. So constraint type, no matter what. So in both cases, we have a constraint type boundary condition there, right? No matter what happens, right? Whether we have steel or plastic, the left side of these structures are not going to move because we have a fixed support, right? So in both cases, the fixed support is applying the same effect because constraint types don't really care about the material properties, but load types do. Okay. Any questions on this so far? Okay. So strictly speaking, a load type boundary condition is not a requirement to run an FEA. So you can run an FEA simulation without a single load type boundary condition. Remember I mentioned earlier that you can run an FEA simulation with displacement type constraints, right? And so if you run your simulation and all of your constraint, you have a fixed support and a displacement type boundary condition, you can actually run a simulation on that. So there won't be an error, and ANSYS will let you run it. But so that means you can run a simulation without any loads at all. Now, for the most part, for most simulations and most physical applications, you're going to apply a load naturally, just because that's kind of how these that's a lot of times that's kind of how we think about these situations, how we model them. Okay. So a lot of times, especially with the activities and especially with the projects, you're going to have a load type boundary condition that just comes out just naturally. And so it's likely going to be there, but strictly speaking, a load type is not required for a solution, unlike the constraint types. Okay. Okay. And kind of along those lines too, when you're choosing a load type boundary condition, you have a lot of options. And so, you know, you can choose a pressure boundary condition, a force, a bearing load, you know, lots of different things. The most important consideration that you have to make when you're choosing a load type boundary condition is, you know, you have to be consistent with the physical situation that you're trying to model. And so some of you have kind of already kind of you know, thought about this because, you know, I've kind of talked to some of you, right? So this is the decision, you know, whether you use a force boundary condition or a pressure boundary condition. You can achieve the same results with the force boundary condition applied on a certain area and a pressure boundary condition applied on the same area, right? So you can get the same results for both. But which one kind of makes more sense with how you kind of intuitively understand your model? It's going to be different, right? So for the previous activity that we just did on the bike crank, a force boundary condition makes a lot of sense because, you know, when we think about, you know, applying a force on a bike crank, we think of it in terms of, you know, pounds and newtons and things like that. Okay. Versus another application, you know, maybe you're thinking about, you know, the force that a pressurized pipe is going to be exerting on a pipe wall, right? And so in that situation, you think of the loading in terms of pressure more so than force, right? And so, you know, there's no one load type that's better than the other ones for a general situation. There may be some that are more niche. And so, you know, someone asked me last time about what a bearing load is. And so a bearing load actually, you know, would be pretty good for some situations. Okay. It's just think about the physical situation you're trying to model and think about kind of what makes the most sense in terms of how do I kind of incorporate this into my FEA, you know, in the way that kind of makes the most sense. All right, any questions on this so far? Okay. All right, so for the last thing that we're going to talk about today is some practical considerations for applying your boundary conditions. So now that we kind of know kind of the purpose of the boundary conditions and kind of the different types of boundary conditions that exist, you know, I think, you know, for you guys as you know, for this class where, you know, where we're mostly just focused on, you know, how do we use ANSYS in kind of a professional and kind of a practical way. You know, when we think of boundary conditions, you know, you want to do them in a way that kind of makes sense. That's not going to lead to any errors. Okay. So ultimately, you know, the idea with boundary conditions is, you know, you should apply boundary conditions that best match or are most consistent with the physical situation you're attempting to model. So whatever forces are going to be affecting your geometry or wherever it's fixed or wherever it's constrained, you want to make sure you encode all those or incorporate all of those into your boundary conditions. You have a boundary conditions representing each one, okay? Because boundary conditions is an interesting topic because unlike the meshing, so with the meshing, you know, sometimes ANSYS will tell you when your mesh sucks. And so if your mesh sucks, then ANSYS might tell you, or sometimes it's kind of very obvious just by looking at the meshing. For boundary conditions, especially for some more very complex cases, it's very easy actually to select the wrong boundary conditions or apply the wrong loads or to forget a load or to apply, you know, a load in the wrong location. And ANSYS will run your simulation. But you know, it's not going to tell you an error or it's not going to tell you that something's wrong. Because it's you know, the assumption that ANSYS is making is that, you know, when you apply boundary conditions that, you know, you've kind of thought about it and you know kind of exactly what you're doing. ANSYS is just going to give you the result of whatever boundary condition that you apply. So there's going to be no obvious error. Besides from the obvious, you know, making sure that you have a fixed support. If you don't have a fixed support, then yeah, ANSYS will tell you that. But besides that, you know, if there's no error, you know, when you apply boundary conditions incorrectly, because it's mostly human error. So for example, if we think back to our bike crank, right? We have our bike crank that looks roughly like this, right? We have our 3 holes on this side, right? So those are fixed. If you apply the force in this direction, okay, that's kind of what we kind of concluded at the end of the activity last time, that applying the load in the y direction is going to maximize the amount of stress, right? Because we're putting it in bending. Versus, right, if we take our same bike crank, we have our fixed supports here. If you apply the load in kind of an oblique manner, so let's say that you apply it kind of diagonally like that, right? ANSYS will look at both of these situations and they'd be like, yeah, this looks great. You know, I'm going to give you the simulation results for both. But we know just based on our intuition that the situation on the right is not going to be, that's not the most dangerous situation, but that's not consistent with the goal of our simulation, because this is not going to have the maximum amount of stress. So I would say, you know, the situation on the right has incorrect boundary conditions, because this is not consistent with, you know, what our goals of the study are, which are to, you know, find out what the maximum stress is in this bike lane possible. And you know, I kind of paused a little bit writing that because, you know, you're not aiming to maximize stress in every FBA simulation. It's just that in that activity, you know, one of the goals was to find out, you know, whether our bike crank was going to fail or not if we had a 100-pound force, right? And the easiest way for it to fail with a 100-pound force is to put it in bend. Okay. So whether a boundary condition is correct or incorrect is going to depend on your application. It's going to depend on your situation. But just know that, you know, ANSYS, that's not something ANSYS is going to check for you. It's not something that's going to give you an error message for. That's something that you kind of just have to kind of check yourself and you know, and just kind of make sure that you're on top of it. So that's the first piece of advice, or the first, I would say, practical consideration for boundary conditions is to make sure that, you know, everything that you choose or all your boundary conditions is physically consistent with the, you know, with the real life situation you're trying to emulate. So every single force that's going to be applied onto your system, every single source of pressure, every single constraint, fixed constraint, displacement constraint, you want to make sure you include all of it in the boundary conditions. Okay? Otherwise, if you don't include everything, or you choose the force value incorrectly, or the direction of the force incorrectly, the results you get are not going to be reliable. Okay. So actually, for a lot of practical situations on very complex geometries with complex loading, besides the meshing, I would say meshing is usually the most frustrating. But besides that, the engineers usually spend a lot of time thinking about, how do we apply these types of boundary conditions. Okay? And I will say that, a lot of times there is no best way to do this. So for all the situations that we're going to be doing in this class, it's usually pretty obvious. Just because I tell you to apply forces in certain places. But for a lot of situations, it's not going to be as straightforward. Okay. So for example, I think the most common situation of this is any kind of forces or any kind of pressures that are kind of unevenly distributed across a surface. Right, so even something simple. So let's say that you have a water bottle, right? And so you're holding up the water bottle with your hand. And so intuitively, you would think that you can apply just a uniform force around the outside of the water bottle to represent your hand gripping it. But that's not 100% correct, because your hand only applies forces wherever your fingers are. And so if you wanted to be truly accurate, then you would actually trace out, where your fingers are making contact with the water bottle and only apply the forces on those locations. But that's pretty difficult and actually very tedious to do in reality. So a lot of times you're going to have to make concessions and say that, I'm going to approximate this as a uniform force across this entire surface. But where you draw the line in terms of where you make concessions and where you approximate things, that's something that you kind of have to reason with yourself and see if that's actually something that's reasonable considering your situation. Okay. So this first point here may seem obvious when you read it. It's like, yeah, you don't apply a force in the wrong direction, but a lot of times it's more difficult than you think to think of like an organic physical situation and to basically turn it into a math problem and turn it into the boundary conditions that you're going to. Okay. Any questions on this so far? Okay, number 2. The number 2 practical consideration is that you do not need to apply a boundary condition on every single surface of your model. So again, this one might be obvious, and this probably hopefully something you picked up from our last 2 activities, but we did not apply boundary condition on every single surface, right? That doesn't mean that one's not needed there. So mathematically and technically speaking, every single surface on an FEA model needs to have a boundary condition in order for it to be solved, right? But that doesn't mean that you have to explicitly apply one. So if you don't apply a boundary condition on a particular surface, then ANSYS will apply one by default. And what is that default boundary condition? That default boundary condition probably does exactly what you intuitively are thinking. It's called the stress-free boundary condition. So the stress-free boundary condition basically says that there's no external effect. There's nothing pushing against us. There's nothing constraining it. And so the external force there is essentially zero. Okay. Mathematically, that is actually important, to solve the equations. And so, because there is a term in the FEA equation that does that. But that's just kind of for your information. So, if there's no external effect or there's no force or anything contacting your model at that certain point, just don't apply any boundary condition there, and ANSYS will just apply the stress-free boundary condition. Okay, so that's nice because then that just leaves you to focus on just the places where you do have some kind of external effect, and you can incorporate that in that boundary. Okay, number 3. The number 3 piece of advice is to apply the boundary condition on as wide of a surface as possible. Of course, within reason, and so don't apply anything on a large surface if it doesn't need to, right? But what I mean by this advice here is that generally, if you have the option to apply the boundary condition on a face versus an edge versus a point, a face is more preferable than an edge, and an edge is more preferable than a point. So I mentioned this here just because, sometimes, when we think of kind of boundary value problems mathematically, oftentimes forces are applied at a point. And so that kind of, intuitively, you may want to apply a point load onto an FEA simulation. Generally, you want to avoid it because, when you apply a force at a point, you kind of concentrate a ton of force or a ton of load at a singular point in your mesh. And sometimes, if the loading is high enough, that can cause some numerical issues as well. Same thing for an edge. And so, if you can, try to apply all your forces on faces. It can be a very small face, a very narrow face, but almost anything is better than an edge or a point. Because sometimes it can cause some issues. And you kind of want to avoid those as much as possible. Okay. Now, this doesn't mean that you apply a force in the wrong location because you're trying to put it on a face, right? If it makes sense, like you're only applying a force at the very, very tip, or very, very end of the model, sometimes it makes the most sense physically to use an edge or to use a point. So don't distribute a force over a face just for this, but so you kind of have to balance this with point number 1 in terms of what makes sense most physically versus what's going to be the easiest to. Okay, Any questions on this? Okay, so last point that I'll make here, and I guess we'll be pretty early today. Is that, it's possible to apply multiple boundary conditions on the same surface or the same location. So you're not locked to just applying one load to one location, right? So usually this is most common when you're applying multiple loads to the same place, right? In fact, that is quite common. So having multiple sources of loading. So you can apply it on the same surface, and so there's no exclusivity agreement here. Okay, but if you're going to apply a constraint boundary condition and a load type boundary condition at the same place, the constraint type boundary condition will kind of supersede or take priority over the load type. And in fact, if you apply certain types of constraint type boundary conditions, it may render the load type boundary condition completely useless. Okay. So for example, let's say that you apply a fixed support at the same location as a force. So let's say that we have a beam. We have a fixed support here. Here, okay. If we apply a force here, so let's say we apply a force right on top of the fixed support, right? That force is going to want to try to force the beam to deform downwards, but the fixed support there is saying that deformation is going to be zero here. So you kind of have a an unstoppable force meeting a movable object, literally, here in this case, right? But in this case, the immovable object is going to win. And so in this case, the your simulation results, when you look at here, you're going to see zero deformation. Because the constraint type boundary condition that's there, the fixed support that's there, is going to take priority over the force, over the load. Okay? So a lot of times, you want to avoid situations like this. And so if you have a situation where, physically you think there should be a force and a fixed support, or a force and a constraint applied at the same location, you may want to kind of rethink how you're modeling your situation, because that force is effectively going to be useless because it's not going to be affecting really much of it. Okay. All right. Any final questions on this? Okay, all right, so I guess we'll end a bit early today. So when we come back on Thursday, we'll be going over kind of what I consider the last aspect of the basics of FEA, which are material properties. And so we'll be going over that. And then we'll just be going. So thank you guys for coming today. If you have any questions on the activity or just questions in general, I'll stick around until 6:45. But if not, hope you guys have a good evening, and I will see you on Thursday. So you guys.
Capture. What up? I guess feeling pretty good. Tired. She's not being, just the life, I guess we selected for ourselves, working in the study of night classes, a bunch of goobers. That's life.